Somehow we lost connection over here. Let me get you back up and good to go. 1 second. Cool. 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 All right, great. We're back in business. Okay. Sorry about that. So anyway, suppose this is equal to that. And well, I feel like we don't even, no, that's, so let's go ahead and write dg dt in terms of only g. What does that even mean? Well, I'll remind you, we know that dg dt is equal to negative 0.2 times g plus 0.1 times a. But we also know that g of 0 plus a of 0 is equal to 20. Now, that might not feel like it's super helpful, but we have to know more than that. So we talked about how the function is g of t plus a of t is always constant. So once you know that g of 0 plus a of 0 is equal to some number, that's the number for any value of t. So g of t plus a of t, regardless of what input we're putting in, is always equal to 20 in this situation. So we know that g of t plus a of t is equal to 20. So we can replace a here with 20 minus g of t. So we can actually write this as dg dt equal to negative 0.2 times g plus 0.1 times 20 minus g. Or rewriting it, we've got dg dt equal to, let's see, negative 0.2 minus 0.1 is negative 0.3 times g, and then 0.1 times 20 is just plus 2. Why do this? Well, what I'm trying to actually do is circumvent having to solve this using eigenvalues and eigenvectors, although we're going to come back and do it that way too. So, but just kind of show you that sometimes you can do something interesting here. So I want to point out, hey, look, we have a differential equation, and we could totally separate this. Or we could do it as a first order linear. Do you guys remember that from 17b? First order linear differential equations with an integrating factor? You might not have learned it. So that's why I'm actually asking if you remember, because some people don't teach it. If that sounds familiar to you, you could solve this doing that, but we're not going to, but I just wanted to mention it. So let's solve this differential equation by separating variables. So we're going to solve dg dt equal to 0.3 times g plus 2 in a more kind of 17b sort of fashion by separating variables. So let's take a look and see what we've got here. So this is where things, you have to be a little bit careful here. We really just have to multiply both sides by dt and say we have dg equal to, and I forgot the negative sign here, apologies, negative 0.3 times g plus 2 times dt. And then to separate, the g is on the left and the t is on the right, we do have to divide by negative 0.3 g plus 2. So we're going to rewrite this as 1 over negative 0.3 g plus 2 dg equal to 1 times dt, or just dt. And then we're going to integrate both sides. Like 1 there. Okay, go ahead. Take some water. And to differentiate that. The right-hand side isn't too bad. Left-hand side, it's kind of looking like we're not going to, but you could think of making this your u, and then your integral of 1 over u is the natural log of the opposite value of u. Except I think we usually ignore the opposite values here, because yeah, we do. Because it all works out in the end is why we ignore the opposite values, is the glossy thing we'll say and not deal with it too much. So here we're going to get the natural log of negative 0.3 g plus 2, but it's not quite right. If you took the derivative of this, you'd have to use the chain rule. And you get 1 over negative 0.3 g plus 2 times the derivative of the inside, which is negative 0.3. So we have to divide by negative 0.3. And then things are looking all right. Now we're going to solve for g. So we're going to multiply both sides by negative 0.3. We're going to get the natural log of negative 0.3 g plus 2 equal to, we're going to multiply both sides by this negative 0.3, so we get negative 0.3 t plus a constant, because a constant times a constant is still a constant. Now we're going to keep solving for g. We're going to e both sides. So I'm going to say e to the all of this is equal to e to the all of this. So we're going to get negative 0.3 times g plus 2 on the left equal to e to the negative 0.3 times t plus c, or times e to the c, right? Instead of writing that like that. And then, sure. Then we usually call this a new constant. I prefer to call it a. I don't have a good reason other than that's how I learned it. So we keep solving for g. We're going to, how do I want to do this first? Yeah, let's go ahead and subtract it from both sides and say negative 3/10 times g is equal to a times e to the negative 0.3 times t minus 2. And finally, multiply both sides by negative 10/3 to get g equal to, well, a constant times negative 10/3 is still a constant, a e to the negative 0.3 t, and then negative 2 times negative 10/3 is positive 20/3. Oh, we're not quite done, though. That's not my final answer. Because we know how to find the constant. Because our initial condition was that g of 0. Did I have an initial condition? Now I have to double check my notes back here. Oh yeah. No, we didn't. We did not have an initial condition. I failed to say it. Apologies. Interesting. Yeah. So if we're given, let's just not try to squeeze things in. Just a bad habit I'm trying to break. So part E, if we're given that g of 0 is equal to 2, let's find the particular solution. So let's see, if we do this, that's not too terrible to do. We're just going to say that 2 is equal to a times e to the 0th plus 20/3. So a here is going to equal 2 minus 20/3. So that's going to be what, negative 14/3, I think? I feel like I'm making some, I feel like my brain is making errors that they should not be making. Let me double check here, just I feel like I'm saying something stupid. No, I'm not. I'm just, yeah, okay. Sorry, sometimes your brain does weird things. Well, at least mine does. So 60/3 minus 20/3 is equal to 40/3, which is our A. So our solution for this situation is that g of t is equal to 40/3 e to the negative 0.3 t plus 20/3. Okay, it feels kind of like a lot of work. I will mention we could have done the other thing. We could have written the matrix, found the eigenvalues, found the eigenvectors, written the general solution, plugged in the initial conditions, and then found the actual solution. It's probably on par with that level of work, I would say. My opinion is it's just kind of interesting to see that we could do this a different way. But now here's what I think is actually interesting about this, is that, well, we solved part of it, but what about the other part, right? If you go back, right, we had a system of two differential equations and two unknowns, right? We had dg dt equal to something and dA dt equal to something. Well, it's easy to find A because we know, right, we know that A of t plus G of t is equal to a constant, specifically 20. Oh, there's some flashing lights outside. I hope everything's okay. Well, looks like they're taking care of it, so we will continue on. So we know that A of t plus G of t is 20, so we can just say that A of t is equal to 20 minus the G of t we just found. So here, A of t is equal to 20 minus 40 thirds e to the negative 0.3 t plus 20 thirds. And simplifying this just a little bit, the 60 thirds here minus the 20 thirds there becomes A of t equal to 40 thirds minus 40 thirds e to the negative 0.3 t. And if you, oh, sorry, I can't do that. If you add those two solutions together, I think it's somewhat obvious that adding this to this is going to give you exactly, well, the e part, the e to the t part canceling out, and the 20 thirds plus 40 thirds is going to give you 60 thirds, which is 20. One more question about this situation before we look at a more maybe typical situation for a compartment model. So one thing you might ask here is, sorry, let me kind of move that a little quickly there. Also, if you ever need to see something, I'm happy to like put stuff back on the screen. I just sometimes get going kind of fast. What fraction of this slice of forest is occupied by adult trees as time goes on and on and on? What kind of equilibrium are we approaching if we let this system just continue to do its thing forever and ever and ever? Well, fraction of the forest that's adult trees, we want to know essentially what do adult trees divided by the total, what's that going to do as time goes on and on and on? Well, we're in kind of an easy situation here because we know what the bottom of this fraction is. The adult trees plus the gap is 20 acres. So our denominator starts off just being 20. And our numerator is just what A of t is equal to. So we've got our 40 thirds minus 40 thirds e to the negative 0.3 t. And as time goes towards infinity, e to the negative something times time, that's going to get smaller and smaller and smaller. So as time goes on and on and on, we're getting 40 thirds divided by 20, which is 2 thirds. So the forest will be 2 thirds adult trees, or I should say 10 to 2 thirds adult trees and 1 third gap. What this should also tell us is if you solve this system the other way, finding the eigenvalues and eigenvectors, one of your eigenvectors would be the eigenvector 2, 1 or 1, 2, because these things are in a 2 to 1 ratio. Adult trees to gaps, right? 2 thirds to 1 third, 2 to 1. That's what one of your eigenvectors would have to be, and your eigenvector associated with like your more dominant eigenvalue. Should we do it the other way? It's okay to say no. Like we don't have to do it the other way. You guys are like, yeah. What we've been doing for like the last couple weeks. I don't know. I think it's interesting to see it this way, which is why I talked about it. And I certainly, of all the people who teach 17C, I could maybe see Dr. Lewis being more likely to talk about this, but probably not, to be really honest. So all the stuff I just said, maybe not super necessary. Sorry, sometimes we get off on tangents, but let's bring it back around and talk about how we would do this the other way. So let's go back and say, well, looking at our system, and I'll try to walk through this relatively quickly because we have already kind of done it. So we had our equations, which were, pardon me, let me write them down again. We had dg dt equal to negative 0.2 times g plus 0.1 times a, and dA dt equal to the opposite, 0.2 times g minus 0.1 times a. And this situation is unique because we have equations that add to 0. That's not your typical situation. So if we write this as a matrix equation, we have dg dt, dA dt, and I'm doing a good job of making my A's and my G's look different, equal to negative 0.2, 0.1, 0.2. Oh yeah, 0.1. This is why this situation is kind of weird. One of our eigenvalues is going to be 0. How do I know that? Aside from having done this problem before. I know that, and you should learn to know it because these two rows are multiples of each other. If you happen to have a situation where, like, yeah, like for example, just to kind of like if you had something like this, if your matrix was 1, 3, -2, -6, automatic indication that 0 is going to be one of your eigenvalues because your rows are or your columns, either way you want to say it. Your rows are multiples of each other, or your columns are multiples of each other. Let's see it. If I was finding the eigenvalues here, I have 1 minus lambda, 3, -2, -6 minus lambda. Find the determinant of that matrix. It's going to be 1 minus lambda times -6 minus lambda minus 3 times -2. And if you multiply this out, we're going to have, let's see, lambda squared plus 6 lambda minus lambda minus 6 plus 6. Oh, yeah, those cancel. You've got lambda squared plus 5 lambda. You've got lambda times lambda plus 5. So lambda equal to 0 is one of your eigenvalues. That's always true if your rows are multiples of each other. It's not often true in this class. Most of the time in this class, you should be getting non-zero eigenvalues that are different from each other. Very, very, very rarely do we get 0 or the same eigenvalue, although you can. Okay, you can go away. So back to this one. Finding the eigenvalues, we know one of them is going to be 0. So we have the determinant of negative 0.2 minus lambda, 0.1, 0.2, negative 0.1 minus lambda. That's going to be negative 0.2 minus lambda times negative 0.1 minus lambda equal minus 0.1 times 0.2. So let's see, multiplying this out, we have lambda squared. We have plus 0.1 lambda plus 0.2 lambda for a plus 0.3 lambda. And then we have the things that are going to cancel out. Negative 0.2 times negative 0.1, which is 0.02 minus 0.02. So this factors as lambda times lambda plus 0.3 equal to 0, which we get lambda equal to 0 and lambda equal to negative 0.3. Well, that's a good sign. Remember how our solution had an e to the negative 0.3 times t in it? That's boding well for us. For me especially. There's always a slight worry when you say something's going to work out the same, when you start doing, you're like, this better work out the same, otherwise I've made an error somewhere. Okay, so let's go ahead and find the eigenvectors. So for lambda equal to 0, it's a little more nicely here. We have our matrix, negative 0.2, 0.1, 0.2, negative 0.1, times the eigenvector we're looking for, equal to 0 times the eigenvector we're looking for. I should ask, I assume Dr. Lewis has done this a few times in class now. Does he prefer to do it this way or the way where it's like a minus lambda I times the vector equal to the 0 vector? Okay, great. Both is good. Okay. All right. Well, good. That sounds like he's fine with you doing either way, which most people should be. So again, looking at the first equation, I've got negative 0.2 times x plus 0.1 times y equal to 0. Isolating y, I've got 0.1y equal to 0.2x. I would probably multiply both sides by 10 to say that y is equal to 2x. So my eigenvector should be x is 1 and y is 2. Oh, like, didn't I say something about one of the eigenvectors being 1 and 2? Interesting. Then for the other one, lambda equal to negative 0.3. So in this case, we're going to have negative 0.2, 0.1, 0.2, negative 0.1 times the other eigenvector we're looking for equal to negative 0.3 times xy. Again, using the first equation. Be careful. I've helped a few students, not anyone here, but just in general. I've helped a few people when they write this down, somehow they do the multiplication like kind of wrong. I've seen people write like negative 0.2 times x plus 0.1 times y equals negative 0.3 times y. Be careful, right? If you're doing the top row, it's got to be all the top row things. So our first equation is negative 0.2 times x plus 0.1 times y equal to negative 0.3 times x. Or just for the sake of saying it, if you wanted to use the second equation, it would be 0.2 times x minus 0.1 times y equal to negative 0.3 times y. But you almost ever only need one of them. So I always use the first one because it just seems like the one I see first. So adding 0.2x to the other side, I've got 0.1 times y equal to negative 0.1 times x, or better, y equals negative x. So my other eigenvector is going to be 1, negative 1, or negative 1, 1. Either way you want to write it, it's totally fine. All right, let's find the general solution. So general solution at this point is just like remembering a thing, right? There's no work to be done here other than writing down the thing we remember, which is that our general solution, or G of t, A of t, should equal C1e to the lambda 1 times t times V1 plus C2e to the lambda 2 times t times V2. And then literally just substituting in the lambda 1, the V1, the lambda 2, and the V2. So this is going to be equal to C1e to the lambda 1 I said was 0. I shouldn't even be writing 0, but okay. And then times V1, which is 1, 2, plus C2e to the lambda 2 is negative 0.3 times t times V2, which is 1, negative 1. Now we'll use our initial conditions to find the particular solution. Actually, I should say one more thing. Let's actually do one more step here. This I should simplify because e to the 0 is just 1. So this is really C1 times 1, 2 plus C2 e to the negative 0.3 t times 1, negative 1. And then if we use the initial conditions that G of t was equal, sorry, G of 0 was equal to 2. And we know that, well, we know that the total was 20 and they always total to 20. So A of 0 should equal 18 because they have to add it to 20 no matter what time it is. Still true, right? We didn't change the problem. We just changed how we're solving it. But if they add up to, right, if their derivatives add up to 0, their functions have to add up to a constant. And since we said the constant they added up to was 20, well, G of 0 being 2 means A of 0 has to be 18. Also, just if you look back at our previous solution, just to remind you of this, if you look at, now that seems interesting. That seems like a mistake. Now I'm like, A of 0. Sorry. Now I'm looking at my solution here and feeling like I made an error of some sort. I did make an error of some sort. Brain. So I think I see the error. Sorry. Yeah. Sorry. Let's go back for a minute and fix this before I get too crazy here. Yeah, is that right? No, that's not right. Sorry, I'm looking at my notes here for a second. So G of 0 should be 2. So we got to here last time. Did I say something stupid? Sorry, sometimes you get stuck. I said G of 0 was 2. So 2 equal to that. 2 is not, oh my God. Oh my God. 2 is not 60/3, right? Yeah, right. What mistake? I made some stupid mistake that now my brain is not letting me get over. We'll come back and fix that in a minute. Sorry, I'm getting a little too hung up on the details here. Let's not worry about it too much. We'll fix it in the end. So here we've got 218 equal to C1 times 1, 2 plus C2 times 1, negative 1. So we've got the system of equations. We've got 2 equal to C1 plus C2. We've got 18 equal to 2 times C1 minus C2. And if we add those equations together, I'm choosing that because I can see that the C2s will cancel right away. If we add these together, we're going to get 20 equal to 3 times C1. So C1 should equal 20 thirds. And then going back and solving for C2, well, C2 is going to equal 2 minus 20 thirds. And I promise you I can do this work correctly. Multiply this by 3 over 3. Why does that feel so wrong, though? Yeah, C2 should equal, I know why it feels wrong. 6 thirds minus 20 thirds, which is negative 14 thirds. So 20 thirds plus negative 14, 6 thirds, and then 40 thirds plus 14 thirds is 54 thirds, which is 18. Okay, that's right. Yeah, I see what happened there. Okay. Yeah, there was a mistake back here. So now let's go back here and correct that. I apologize. Sometimes mistakes happen. I got a little carried away here and somehow thought this was 60 thirds. That should have been 6 thirds. A should have been 6 minus 20, which is negative 14 thirds. So that should change a few things over here. It's kind of gross to fix. That's a negative 14 thirds. And that means over here, that's a negative 14 thirds, which means this solution should be a plus 14 thirds over there. I don't love that. Sorry about that. I don't try to make mistakes that heinous on purpose. I mean, it's not like it's the worst mistake I've ever made, but I don't try to write confusing things on purpose. Sorry. Okay. So one good thing about doing something two different ways is if you made a mistake doing it one way, you might see you actually made that mistake when you do it the other way, which I'm clearly seeing now. Let's wrap this up. So our particular solution here is going to be that A of t, G of t is equal to our C1, which is 20 thirds, times e to the 0t, which I'm not going to write because e to the 0t is just 1, times the vector 1, 2, plus C2, which is minus 14 thirds, times e to the negative 0.3t, times the vector 1, negative 1. And I think I got my A of t and my G of t out of order because, what else could go wrong? I did. Yep, I totally wrote them out of order. Sorry. Just trying to do all the wrong things to help you really solidify the points here. Not really. I'm really not trying to do that. So writing out our solutions, our G of t is equal to 20 thirds times 1 minus 14 thirds e to the negative 0.3t. And our A of t is equal to 20 thirds times 2, which is 40 thirds, minus 14 thirds times negative 1, so plus 14 thirds e to the negative 0.3t, which after our correction just a moment ago is exactly what we had for our solutions. Kind of neat that you could do it different ways. But again, the other way only really is a product of starting off with something very kind of different, or very specific, I should say, where the two differential equations added up to 0. Apologies for taking you down a long and winding road that was full of mistakes. Let's look at some more typical compartment problems. So let's say we've got the following situation. Let's say we have this example. Below is a schematic example, or description, I should say, of a compartment model. Determine the corresponding system of differential equations. And analyze the stability of the equilibrium 0, 0. Okay, when we say analyze the stability of the equilibrium, what does that mean we need to do eventually? Any volunteers? Right, exactly. We're going to look at the eigenvalues and then make a conclusion. What if it's a stable node, an unstable node, a saddle, a stable spiral, an unstable spiral? Those are kind of the options. It doesn't mean solve the system, right? It just means find the eigenvalues and then look at what the eigenvalues are telling us. Okay, I have to draw the picture too. Sorry. So here's my picture. So I've got my X1 compartment here, my X2 compartment over here, and I have 1.7x going this way, X1, sorry, and 2.1 X2 going that way, and out this way we have 0.6 X1, and going out this way we have 0.9 X2. So even though these compartment diagrams look a little weird at first, writing down what's going on is actually really pretty straightforward. So basically, you look at X1 and say, okay, the rate of change of X1 is just adding all the things going into it and subtracting all the things going out of it. So every arrow that's pointing into it, you add it. Every arrow that's pointing out, you subtract it. So kind of in a terrible way here, I'm going to write this as plus 2.1 times x2 minus 1.7 times x1 minus 0.6 times x1. I'm going to fix that in a minute because this is kind of the worst. Similarly, for the rate of change of x2, well, let's see. What's going into x2 is 1.7 times x1. And what's going out of x2 is 2.1 times x2 and 0.9 times x2. All right, so now we should rewrite this so that it looks like so that we could turn into a matrix, meaning you definitely need to write your variables in order, x1 before x2, even if the x1 coefficient is negative. So we should rewrite this as dx1 dt equal to negative 1.7 x1, and then sorry, oh, I missed, nope, I blew it. Let's just use a new page here. I forgot the other part of the x1 here. So it's negative 1.7 minus 0.6. So my dx1 dt is negative 2.3 times x1 plus 2.1 times x2. And my dx2 dt is 1.7 times x1 minus 3 times x2. I feel like finding the eigenvalues here is going to really, really suck. Well, let's take a look anyway. So we're going to analyze the stability. So we're going to find the eigenvalues. So it's going to be the determinant of negative 2.3 minus lambda, 0. Wow, where's my, something is going on inside my head, I feel like. 2.1, 1.7, and negative 3 minus lambda. Interesting here. So that's going to be, let's see, negative 2.3 minus lambda times negative 3 minus lambda minus 2.1 times 1.7. I'm not thrilled about this. Let's keep going though. So I've got lambda squared. I've got plus 3 lambda plus 2.3 lambda, which is plus 5.3 lambda. I've got negative 3 times negative 2.3. That's going to be, what, 6.9. And then 2.1 times 1.7 is going to be, I think it's like 3.57. You can use a calculator. It's not a crime. Can I use a calculator? Maybe. 2.1 times 1.7. Yep, 3.57. So then putting it all together, we have lambda squared plus 5.3 lambda. And then 6.9 minus 3.57 is, geez, 3.33. Looks like it. I bet this doesn't factor very nicely. I bet we need to use the quadratic formula. Now, here is something that might be worth knowing here. No, we'll say that first. So let's just write it out. So lambda is going to equal negative 5.3 plus or minus the square root of 5.3 squared minus 4 times 1 times 3.33, all divided by 2. Okay, so there's two questions to really answer here. Question 1, is my discriminant positive or negative? So what's going on with 5.3 squared minus 4 times 3.33? Without using a calculator, I think we can easily enough see that that's going to be positive. 5.3 squared is bigger than 25. 4 times 3.33 is like 13-ish. 25 minus 13 for sure positive, which means our eigenvalues are real. Now, are they both negative, both positive, or one of each? Well, I know what it isn't. I know they're not both positive because they've got negative 5.3 out here, plus or minus some stuff. Now the question becomes, is the square root of this stuff bigger than 5.3 or not? If it's bigger than 5.3, then negative 5.3 plus it is going to be positive, and negative 5.3 minus it is going to be negative. So we're going to have a saddle. But if that thing is smaller than 5.3, then negative 5.3 plus it is still going to be negative. And negative 5.3 minus it is also going to be negative. So the question is, well, this is in the neighborhood of 25 or 26. This is in the neighborhood of 13-ish. 26 minus 13 is 13, and the square root of 13 is definitely a lot less than 5.3. So this is for sure less than 5.3, which means both my eigenvalues are going to be negative. Which means we have a stable node, also known as a sink. Now, these numbers turned out really ugly because they just made them up in the beginning, and sometimes that happens. But what do I really want to say here? There's a way you can analyze the stability without directly computing the eigenvalues. So, how much time? Yeah, we got time. We got enough time. So I'm going to say something else, which I just want to point out. So a while ago, I kind of mentioned something about how, like, when you find the determinant of your A minus lambda I, the trace and the determinant of the original matrix show up. So if we write our very generic matrix as A, B, C, D, the trace of A, that's the trace, we use a tau, that's equal to A plus D. And the determinant of A, which we use a capital delta for, is A times D minus B times C. And then check out what happens here. When we find the determinant of A minus lambda times I, we end up getting the determinant of A minus lambda, B, C, D minus lambda. When we multiply it out, we get A minus lambda times D minus lambda minus B times C, which ends up simplifying as lambda squared. And then you have minus lambda times D minus lambda times A, which is plus negative A minus D times lambda plus A times D minus B times C. Or as you might write, lambda squared minus the trace times lambda plus the determinant. And that is not a once in a while kind of thing. That is an all the time kind of thing. So whenever you find the determinant of a 2x2 matrix, it's always going to be this format. So in fact, if you find this easier than writing out the determinant of A minus lambda, B, C, D minus lambda, you can jump straight to saying, hey, cool, my quadratic equation here, this is called the characteristic polynomial, by the way. This is always going to be lambda squared minus the trace times lambda plus the determinant. Why is that helpful? Well, we know some things about finding the solutions to this equation. There's my B equal to the negative of the trace. There's my C equal to the determinant, and there's my A equal to 1. So if I now use the quadratic formula here, look at what we get. Our lambdas are going to equal the negative of B, which is the negative of the negative trace, which is just the trace, plus or minus the square root of B squared is the negative trace squared, but the negative thing squared is still positive, so we'll just write the trace squared, minus 4 times 1 times C, which is your determinant, all divided by 2. And knowing the trace and the determinant and how they compare to each other tells you everything about analyzing the stability, the origin. So check this out. First of all, if your determinant is negative, saddle every time. Wow, could I have written the word saddle any worse? Maybe, but that's a pretty good attempt there. Let's try that one more time. Saddle. Why? Well, think about this. If your determinant is negative, then negative 4 times your determinant is going to be positive. The thing inside the square root is going to get larger, so whatever's inside the square root is going to be bigger than tau squared. And if you take the square root of that, it's going to be bigger than tau. Tau plus a number bigger than itself is going to be positive. Tau minus a number bigger than itself is going to be negative. So if your determinant's negative, you automatically have one positive eigenvalue and one negative eigenvalue. There is no other possibility there. Also, I said something else before, which I'll remind you of. The eigenvalues have to multiply to the determinant. So if the determinant's negative, one of them has to be positive, one of them has to be negative. You cannot get imaginary eigenvalues if your determinant of your original matrix is negative, because you're always going to be adding something positive here, so you can't have a negative discriminant. Things get a little bit dicier if your determinant is positive. So if your determinant's positive, you have a few options. First of all, let's look at the trace. So option 1, I feel like I'm trying to squeeze things in here and it feels really stupid. Let's be smart about this, James. Let's write it again here. Sorry. I'm trying not to just write things as tiny as possible. And so, I'll get this again. If your determinant is negative, saddle all the way, every time. I should remind you, this is the determinant of the original matrix, not the after you subtracted the lambdas or whatever. The determinant of the original matrix, negative, saddle. If your determinant is positive, we have a couple cases. So you could either have your trace being negative. If your trace is negative, well, check it out. That means whatever you have over here, you're going to have a negative number plus or minus either something that's real or something that's imaginary. But either way, it's going to be too small to make it so you get the opposite sign. So if your trace is negative, you're living in the land of stability. If your trace is positive, you're living in the land of instability. Now, the only question is, are we stable or unstable nodes or stable or unstable spirals? And that all depends on if the inside of your thing here is positive or negative. So we know that we have a spiral. This is still all under the if you determine this positive situation. We get a spiral if tau squared minus 4 delta is negative. We get a node if tau squared minus 4 delta is positive. This is usually written as delta is greater than tau squared over 4, or delta is less than tau squared over 4. There's a really cool picture in your book that describes this that I don't have up right away, but I feel like I must show it to you because it's really neat. Give me one moment to pull it up. Sorry, I should have thought of this ahead of time, but I wasn't really planning on talking about this, so Let's see, courses. This is this class. 1 second. This is chapter 10, right? Yeah, this is chapter 10 stuff. Okay, cool. Come on, come on, come on, come on. That's not one. You know when you click on a thing and then the web page moves after you click, and so you clicked on the wrong thing? Yeah. Okay. So here's chapter 10, and this is a little bit down the ways, but we're going to find it, and I'm going to show it to you, and it's all going to be happy. Keep going, keep going. Where are you? Sorry, this is what preparation would have avoided, but you know. There it is. This picture. So this picture is exactly showing you all the stuff I just said. If you have a determinant that's negative down here, saddle land. If your determinant's positive, you got a lot of other options. If your trace is negative, you have stability, either a stable node or a stable spiral. If your trace is positive, you have instability, either an unstable node or an unstable spiral. And then this determinant equal to 1/4 the trace squared, which is the thing we wrote over there. If your determinant's bigger than 1/4 the trace squared, making your discriminant negative, you live in the land of spirals. If your determinant is less than 1/4 the trace squared, you live under the parabola, but the determinant is still positive. You live in the land of nodes. It's kind of useful. In fact, it becomes more useful. The reason I'm actually talking about it now is because when we start talking about systems of nonlinear differential equations and using the Jacobian matrix to kind of estimate what's happening in a particular locality, this is kind of how we actually start analyzing the stability of your non-zero necessarily equilibrium. So there's actually, I'm not just saying this because I think it's neat, although I do think it's neat. I'm actually saying this because I do think it's going to be useful for you, not just because it's like, oh, this is cool. Here's another crazy thing James is talking about. No, this is actually will probably be useful when you start talking about the nonlinear stuff, which I did see he was on the agenda for sometime this week or next week. Okay, so I know it's a lot of things to say. All that to point out that in this previous problem that we had way back here, where our matrix looked like this. So just a reminder, so back to the point. Oh, sorry, you can't see what I'm writing. 1 second here. Now it's still not the words. It still might not make this problem much easier to deal with. But let's take a look anyway. So looking back at our differential or our matrix, which was where'd you go? Negative 2.3 to 1.7, negative 3. Our trace is negative 2.3 plus negative 3, which is negative 5.3. And our determinant is still kind of gross. Our determinant is negative 2.3 times negative 3, which is 6.9, minus 2 times 1.7, which is 3.4. I feel like that was a 2.1. 2 would have been so much easier. 2.1 times 1.7, which was, I forget, 3.57. Oh, yeah, there's a way easier way. Okay. Which is equal to 3.33. So determinant's positive, meaning it's not a saddle. Trace is negative. So this is telling us not a saddle. So it's either a spiral or a node. This being negative is telling us it's definitely stable. And then all that's left to compare is the trace squared minus 4 times the determinant. Okay, so yeah, it's still not great, but such is life. But we can see that negative 5.3 squared minus 4 times 3.33 is definitely going to be positive, meaning our eigenvalues are real, meaning we have to have a stable node. And we know that they're both the same sign because whatever this number is here, if it's positive, it's going to be less than the negative 5.3 that was out in front of it in the quadratic equation. Right? If you look back over here, right? This part here, this number here being positive means you've got 5.3 squared minus something, which makes that all smaller than 5.3 squared, which means its square root is smaller than 5.3. So negative 5.3 minus it is negative, and negative 5.3 plus this thing that's smaller than it is going to be still negative. Yeah. Sync. Yeah, yeah, yeah. Yeah. Okay. Kind of a lot. So let's do one more compartment thing, and then maybe we'll talk. Do we have enough time? Yeah, we probably. So let's say this compartment diagram, which looks like this. We've got X here, we've got Y over here. And let's see, what do I have here? Sure. So from X to Y, we have A times X. From Y to X, we have B times Y. Going out of X, we have C times X. Going out of Y, we have D times Y. And we were told that dx dt is equal to negative 2.3 x plus 0.9 y, and dy dt is equal to 0.5 x minus 1.7 y. And our job is to find the values of A, B, C, and D that make this situation work. Well, it's not too terrible. So looking at the system, we can also write that dx dt is equal to, well, let's see, what's coming into x? B times y. What's going out of x? A times x and c times x. So I'd probably write this as negative a minus c times x, because I do like to keep the order the same, plus b times y. And similarly, dy dt is, well, let's see, we have a times x coming into y, and we're losing b times y and d times y. So we have plus negative b minus d times y. And in this system of equations, two of A, B, C, and D should be really, really, really immediate to find. Specifically, you should be able to look at this situation without writing anything down, telling me the values of A and B. A has got to be that, and B has to be that. There's no other choice. So we already know that A is equal to 0.5, B is equal to 0.9, and then we know that negative A minus C is equal to negative 2.3. So if negative A minus C equals negative 2.3, let's get rid of the negative signs and say that A, which is 0.5, plus C is equal to 2.3. And then C is equal to 2.3 minus 0.5, which is 1.8. Same way we find D, negative B minus D is equal to negative 1.7. Multiplying both sides by negative 1 and replacing B with 0.9, we have 0.9 plus D equals 1.7. So D is equal to 1.7 minus 0.9, which is 0.8. So this is pretty straightforward once you see what's going on. Yeah, we can fit this in. Okay. I just find the thing I'm looking for. Yeah, okay. So the non-homogeneous system of linear equations kind of sucks at first. But the good news is it's actually nothing new. The bad news is there's a process to seeing that it's nothing new, which can feel a little confusing the first time around. But let's go and take a look at that and I'll hopefully get to deliver the good news before we end class. So let's say we have the following non-homogeneous. What does that even mean? Linear system of differential equations. And here it is. It's dx1 dt equal to negative x1 plus 4. dx2 dt is equal to x1 plus 2x2. Or written, well, actually not yet. So here's one way to think about whether or not something is homogeneous. If something is homogeneous, it usually means like identically 0 is a solution. And that is not true here. If you set this whole thing equal to 0, 0, you don't get that x1 is 0 and x2 is 0. You get that x1 is 4 and x2 is, I think, negative 2. So usually just means 0, 0 isn't the solution that it typically would be. Or if you're writing things in terms of matrices, it means you can't just write the equation as a matrix A times your variable vector x. You have to add on some other non-zero vector at the end, which is what we're going to do. So as a matrix equation, it's dx dt, or if you prefer, you can write it as, the actual dx1 dt, dx2 dt, equal to the coefficient matrix. Now, don't get confused here. My coefficient matrix is negative 1, 0, 1, 2 times x1, x2 plus the constant vector over here, 4, 0. Or as you might write this, dx dt is equal to the matrix A times the vector x plus the vector b. So in a homogeneous system of equations, of differential linear equations, your b vector would be 0, 0. It's not here. Okay. The process here is a little challenging the first time around, but the good news is when you actually do this, the way you're going to solve it is essentially by just ignoring this. You're just going to solve the system like you usually would, find the eigenvalues and eigenvectors, and in the very end, you kind of just add on what you need to add on. But I don't remember exactly how to do it without having done it before because it's not something I keep in my mind. So let's go through the process. It's a little bit lengthy, but we will get through it before the end of class at 1:30. So first step, find the equilibrium, which will not be 0, 0. But still easy enough. We just find it by setting each of the equations equal to 0. I put that. Oh, sorry. If you can throw your name on here. I didn't mean to forget this passing around, you guys. That's all I do. So, so find the equilibrium. So negative x1 plus 4 equal to 0 gives us x1 equal to 4. And then x1 plus 2x2 equal to 0. We plug in 4 for x1. We get 4 plus 2x2 equal to 0, which means x2 is equal to negative 2. And we usually write these with hats. So we're going to say that our equilibrium is x1 hat comma x2 hat equal to 4 comma negative 2. And then the rest of this process, unless your instructor asks you to do it, you usually don't have to do all the stuff we're about to do, but we do need to do it this time to kind of make it make sense. So then we're going to make a substitution. The idea really is kind of like when you did like U substitution with integration. We're going to make a substitution so that we'll have a new system of linear differential equations that's pretty much the same, but has 0, 0 as its equilibrium instead of 4, 2 or 4, negative 2, because we know how to solve that other system. So we're going to say y1 is equal to x1 minus the x1 equilibrium, and y2 is equal to x2 minus the x2 equilibrium. Because the equilibrium for this one should be 0, 0, because the equilibrium for x1 and x2 is 4 and negative 2. So here we're going to say y1 is equal to x1 minus 4, y2 is equal to x2 minus negative 2. And then we're also going to solve it for x1 and x2 just so we know what they're equal to because we need them. So this is also going to tell us that x1 is equal to y1 plus 4, and that x2 is equal to y2 minus 2. All we're really doing here is we're rewriting the system in a new way. And what we're working through right now is showing that these two systems essentially have the same differential equations. Let me show you what I mean. So from here, sorry, we're going to take the derivative of both sides. Oh my gosh, if I can move this piece of paper at all. So for y1 equal to x1 minus 4, this is step 3, we're going to differentiate both sides. So we're going to say that the derivative of y1 with respect to t is equal to the derivative of x1 with respect to t minus the derivative of 4, which is 0. But then, so this feels like it's kind of just working back on itself, but just watch for a second. We know that dx1 dt is exactly equal to negative x1 plus 4. But negative x1 is equal, sorry, x1 is equal to y1 plus 4. So this is really negative y1 plus 4 plus 4, which is just going to be negative y1. And similarly, if we look at y2 equal to x2 plus 2 and differentiate both sides, we're going to get dy2 dt equal to dx2 dt plus the derivative of 2, which is 0. dx2 dt, looking at my original equation, is x1 plus 2x2. Plugging in that x1 is equal to y1 plus 4, and x2 is y2 minus 2. We end up getting y1 plus 4 plus 2y2 minus 4, or just y1 plus 2y2. Here's the point of all this. All this tells us that our system of differential equations for the y's is exactly what we thought it was going to be. We have dy1 dt equal to negative y1 and dy2 dt equal to y1 plus 2y2, or as a matrix, dy dt equal to the matrix negative 1, 0, 1, 2. The same matrix as before, but now with no extra part added on. So this system of equations essentially has the same derivatives, but now it's a homogeneous system. We know how to solve this system in the usual way with the eigenvalues and eigenvectors. So then we can solve this system, and then after we solve this system, we can go back and rewrite what the x's are, because we know that whatever y1 is, x1 is y1 plus 4. And whatever y2 is, x2 is y2 minus 2. Or essentially, we're going to take our general solution to this other thing, and we're going to add on the equilibrium to it. That's all there is to it, really. So later on, when we do this again on Thursday, because we will, when we get to this point here where we see this non-homogeneous system of equations, instead of doing all the stuff we just did, all we're going to say is, hey, look, I'm going to look at that matrix A. I'm going to find its solution in the usual way, finding eigenvalues and eigenvectors and probably some constants maybe. And then after I find that solution, I'm just going to add on the new equilibrium to it. That's all there is to it. It kind of feels weird at first. It definitely felt weird to me the first few times I did it, but after you do it enough times, it's like, okay, I kind of see what's going on here. So let's do it. Well, I picked an easy example on purpose. What are the eigenvalues of my matrix? Right, negative 1 and 2. We know that because there's a 0 up there or down there. So my eigenvalues are, let's use a new piece of paper, James. Let's get crazy here. Ugh. Maybe, why is it so hard sometimes? So for the matrix A equal to negative 1, 0, 1, 2, our eigenvalues are lambda 1 equal to negative 1, lambda 2 equal to positive 2. Let's find the eigenvectors. For lambda 1 equal to negative 1, we're going to have negative 1, 0, 1, 2 times the vector we're looking for equal to negative 1 times the vector we're looking for. The first equation does not help us. Negative 1 times x1 equal to negative 1 times x1 is no help. So we use the second equation and we get 1 times x plus 2 times y equal to negative 1 times y. And right. And then subtracting 2y from both. Oops. Oh, every time. Keep forgetting this plug doesn't work. It's the day of failures. Yes, I know it's a very